stop and do this one lecture. So we're barreling along, right, in control systems. We introduced it in the first chapter, and then in the three ensuing chapters, we went over 3 different performance criteria, right? Stability, transient response, and steady state response. So those were our 3 performance criteria. And so now we're getting to the point where we're ready to start designing a controller to meet these criteria, these performance criteria. Now, we're going to take one lecture to do a little bit of math. And you guys don't take any math that is specifically complex analysis. Actually, there's another student who is a double major, math and mechanical engineering, and he took a complex analysis course, and in my robotics class, he was like, yeah, this is all familiar stuff. So, but you guys don't do any of that stuff in your classes, so I'm going to kind of review complex analysis for us to get us prepared to do this controller design, which requires a little bit of thinking in terms of complex analysis. It's not like a whole lot. So we're going to do all of complex analysis in one little lecture. But actually, we're going to only do like the first 3 pages of this. The other stuff doesn't matter quite as much. So we're just going to kind of hit the things that we need for now and go from there. So a complex function got to be able to write on this one. So a complex function, f, maps a subset of the complex plane to the complex plane. Okay? So f is a map from complex to complex. For instance, a complex function f can map a single complex number, s0, to another, s1, which is equal to f of s0. So it's just like a real function. If you give it a real number, if you give a real function a real number, it'll give you a real number back, right? Okay. Complex function, you give it a complex number, it'll give you a complex number back. You guys have seen complex functions before. For instance, what about the function, what about the function all of my user-defined stuff I have to like manually insert, which is really annoying. My computer going to crap in the middle of the semester was like huge setback for me. So like, what about the function f of x equals the square root of x? So even if this is a function that maps, maybe x always has to be real. Maybe we define f to be a function that only accepts real numbers here. If you plug in a negative real number into this, it's going to come out complex, right? It's going to come out imaginary. So we've encountered this idea before. And if you put a complex number in there, it could also be, that would be valid too. So complex function takes a complex number in, gives you a complex number out. Now, remember, a complex number has real numbers as a subset, right? So complex numbers include real numbers, right? I'm seeing a couple blank stares. Complex numbers have a real part and an imaginary part, right? So these are all the reals. This is actually represented by a real number. When you combine them together, you get a complex number. So if your imaginary part is 0, then this goes away, and you just have a real number. So therefore, the reals are a subset of the complex numbers. Okay. So we're going to actually ignore the stuff about curves and ignore the stuff about contours. Okay? And we're just going to focus on complex functions. Complex functions are of interest in control theory because transfer functions, one of the central mathematical objects of control theory, are complex functions. That's why we care about them. Transfer function, h of s, takes in s, which s is a complex number, right? And it gives you back something in terms of ratio of s polynomials, right? Which is also complex. So we've done a lot of work with complex functions. So the utility of mapping the complex plane is especially important for root locus design. Let's do an example of a mapping of a single point. So map the complex point s equals 1 plus j3 with the transfer function, which is a complex function as we covered, shown. Sometimes we say that we are evaluating the transfer function at the point s equals 1 plus j3. So I think you guys can do this. I believe in you. Can you help me out? So just plug 1 plus j3 in wherever we see an s, right? 1 plus j3 plus 4. 1 plus j3 minus 1. So what is the numerator? What does that come out to be?
5 plus j3.
Yep, and the denominator? Yep. So we can we can rationalize this by multiplying the numerator and denominator by j, right? And so what does the what does this come out to be then in terms of, so what does the real number come out to be? So the denominator is -3, and so the numerator, so we'll do another step. You guys want me to do another step? I'll do another step. Okay. So it's going to be j times 5 plus j3 divided by -3, because j times j is -1. And then let's distribute the j. So we're going to have -3. I'm going to move this term here. J times j is 3. J times j is -1 times 3 is -3. Plus j5. So just sort of flip-flop them to write the imaginary one second. And these are still divided by -3. So what is the real part?
1.
And what is the imaginary part? Yeah. -5/3. So that's our answer. So that's pretty straightforward. Stuff that we've seen before. Just kind of like revving up some neurons. So now we're going to.
Sorry, quick question.
Yeah, what's up?
What is that number? What is that again? That's like mapping where stability falls at point 1 plus j3.
What this is evaluating the transfer function. So I didn't say why we were doing it. I just wanted to. we're going to be evaluating transfer functions at points. We haven't quite yet. In the root locus chapter, we're about to start. We're going to start doing this. And so I want us to be comfortable doing this.
Points for argument's sake now are just arbitrarily picked.
Yeah, we haven't chosen, we haven't motivated why we would need to do this yet, but we're going to need to do this. So, now, let's do this geometric interpretation of complex functions. So, it is often helpful to interpret the complex mapping of a point or a contour geometrically. We're not going to consider contours. Contours are important if we do, well, it will be geometrically. Contours are important if we do some other control theory techniques. Root locus doesn't require a lot of that. So let us consider a transfer function, h of s, with complex zeros, zi, complex poles, pj, and real scaling factor k. Okay. Consider each factored term of the transfer function in terms of its magnitude and phase. We can write the magnitude and phase of the transfer function as follows. So the magnitude of the transfer function h of s is equal to the magnitude of k, the scaling factor or gain factor, times the ratio of the product over all of the zeros of the magnitudes of s minus zi, so s minus each zero, divided by the product over j of s minus each of the poles. So what we have in mind here, as we look at this, is a transfer function just like the one we were using a moment ago, rewritten as, minus 1 times s minus, actually no, scratch the minus 1. We have in mind as s minus negative 4 and s minus 1. So this is written, so there's our 0, z1. There's our only pole, p1. And we're going to rewrite it as just a magnitude. And if you take the magnitude of a bunch of numbers that are multiplied together, you can take the magnitude of each number separately. That's a property of taking magnitudes of numbers. And that's what we're doing. We're going to take the magnitude of each term separately. So the s minus zi would in this case be s minus negative 4, and the s minus pi would be s minus 1. And then the gain would be k. All right, so this is the magnitude and phase of transfer function. So the magnitude can be written like this. The phase can be written as the sum of all of the s minus zi angles minus the sum of all of the s minus pi angles, pj, I should say. And this comes from, do you guys remember if we used a more phasor notation or polar representation of the complex number, then this part where we simplified, it's going to be, if we're going to divide the numbers, the magnitudes divide, right? And the phases add or subtract, right? So the numerator is plus, the denominator is minus. Do you guys remember that? Sounds kind of familiar. That's why the phases, the zeros add and the pole phases subtract, and the zeros divide by the poles in the magnitude. So, yeah.
Because now in the magnitude, is it S minus PI or PJ?
Oh yeah, that was J2. I apologize. I changed my index. There we go. So, we're doing this because we're about to make a move with this stuff, okay? We're about to make a move. So, we can interpret this geometrically as follows. Let us consider the evaluation of this at a specific complex value psi, okay? So I'm going to actually refer to this figure up here for this discussion. So psi is going to be some specific complex value that we're going to evaluate this transfer function at, okay? That's psi. So we're representing it in the complex plane because it's a complex number. So, the difference, psi minus zi, and psi, or the difference of psi minus zi and psi minus pi, can be thought of as vectors in the complex plane with tails at zi and pi and heads at psi, okay? So, all of these terms here have s minus zi and s minus pi in them, right? So what we could look at is, in the complex plane, pi, so p1, for instance, is right here. So p1, in this case, if we're going to take s minus psi, oh, sorry, not s minus psi. We're going to take psi minus p1, right? That's what one of the terms would be. It would be psi minus p1. So psi minus p1 is going to be represented in the complex plane as just being a vector that starts at p1 and goes to psi, right? If you thought of psi as being a vector and p1 as being a vector, then their difference is the vector that goes from p1 to psi. That's the way to interpret it sort of as a vector in the complex plane. And the same is for P2. You can think of it as being a vector that starts at P2 and goes to psi. This is psi minus P2, and this is psi minus what?
C1.
Yeah, Z1. Yeah. So these are these vectors, and so this is the geometric aspect. We're thinking of these differences as being vectors, okay? Good. So I just said specifically what those numbers were. So this interpretation we're going to use extensively in the coming chapter. And this is the thing that I really wanted to get us thinking about, is how to think of, so if we're going to, if we're going to think about these as being vectors, their magnitudes are equivalent to what? The lengths of the vectors, right? So in the magnitude equation, what we have is s minus zi magnitudes divided by s minus pi magnitudes. So s minus pi, or the p1 is going to have this vector representation, and the magnitude of it is going to be the length of the vector, okay? And we're going to take the product of the lengths of these pole vectors. We take the product of the lengths of the zero vectors, and you're going to take the product of the pole ones minus the product of or the 0 ones minus, or divided by the product of the pole ones. Can't spit that out. So this one would be psi minus z1 divided by psi minus p1 times psi minus p2, right? And we could geometrically come up with these. So like this is at p1 is at -3 plus j3 plus I3, right? And then psi is at +3 and 4. So we could find the length of that vector that goes between them, and we could plug that in there for psi minus p1. But we're going to use this, we're going to use a little bit to do some, graphical calculation of things. Because we could calculate this based on this, this plot. We could, if you had a scale or a ruler, you could do it really easily, right? But that's not really the value in this. It's the intuitive understanding of how a pole, how its vector contributes and how a zero's vector contributes. That's what we have to think about. And when we do root locus, this is going to be the key thing. And then similarly, I didn't do that. That was just the magnitudes. The phases are these guys, right? So if we wanted to take the phases, we would do psi minus z1, so the phase of that. So you'd have to come down here, you have to take the arctangent of the height over the width, or the imaginary over the real, minus the angle of psi minus p1, which is this angle, right? Minus psi, the angle of psi minus p2, which is this angle. Okay? So that's the sort of geometric interpretation of the magnitude and the phase of a transfer function when you evaluate it at a certain point. Okay? On Wednesday, we'll describe in more detail what that certain point is in terms of the root locus. Because in the root locus, we're going to be doing this everywhere. And this geometric interpretation is really helpful for that. And if you're interested in mapping of complex contours, which is also cool in control theory, there's more of that in this, and then that's what the last 2 pages on this are about. Including, if I do say so myself, a really cool example Mathematica code. You can copy and paste this in. Makes an animation. Pretty fun. So play with that. And yeah, I'll see you guys Wednesday.